Problem-Solver, and today we'll be introducing the technique of moving points. Alright, so to start off, we will want to talk about the projective space. Let's begin with the Euclidean space. So we all know what the Euclidean space is. Just a set of points in the plane. You can have a correspondence between them as x comma y, where x and y are real numbers. So that's our correspondence for any point on the Euclidean plane. Alright, so the idea for the projective plane, here we denote this as r p squared This is known as the real projective plane. So when I say this, I mean that what we do is we take this Euclidean plane, and for any given point, although we did before in our Euclidean plane definition have x comma y as our definition for x, y, and r, we extend it so that if we have a given line, then there's one point at the line on the line at essentially infinity. So what this really means is that given two lines in the same direction, there's going to be one point that lies on them in that direction. And similarly, you can have another two lines here. They'll have the same point essentially. I recommend visualizing it as kind of a circle on the boundary of the Euclidean plane with the circles, but instead of thinking about it like that, you want to think of it as one point on the circle that you're considering. So like you have the two lines that are there, and then in that direction you can say that one of those points on the circle is going to be the point that we're considering. Alright, so the reason that we use the projective plane, the real projective plane, is that it allows us to ensure like there's not as many ambiguities in how the Euclidean plane makes lines function. So for example, in the Euclidean plane, if we had two lines that were parallel, they wouldn't intersect, while if they weren't, they would end up intersecting. So like for example, these two lines would intersect in the Euclidean plane, while these two lines would not. So we kind of have cases on whether or not two lines will intersect. Two lines essentially intersect if they're not parallel, and otherwise they won't intersect. The projective plane, the real projective plane, kind of gets rid of this ambiguity. What happens is that any two lines will end up intersecting at one point. That kind of is the motivation for why we say that there's one point on the end of a given line, one point at infinity essentially. So for this reason, in that same direction, two lines, if they're in the same direction, they'll have the same point at infinity. So for that reason, there's going to be a point at infinity that they intersect at, which means that we don't really have as many ambiguities. So although they don't actually intersect on the Euclidean plane, you can kind of visualize this as kind of converge eventually, like not really eventually, but more like they converge just after everything happens, after we go on and exit kind of the end of the real Euclidean plane. Alright, so that's the definition of RP squared, the real projective plane. So why we consider this is to get rid of the ambiguity, as I previously mentioned. So the ambiguities in the Euclidean plane are a bit are kind of easier to deal with in the projective plane. As a note, you can also, sometimes some people also denote this the real projective plane as p squared sub r. It's more commonly denoted as the previous thing, but just as a note, some texts refer to us as p squared sub r as the real projective plane. Alright, so now there's also a different way that we can consider the real projective plane. One way that we defined it was saying that two parallel lines will end up intersecting as well at a point at infinity. But the important way to think about this is by thinking about a plane and thinking about the lines that go through it. This is kind of the basis of moving points, because it allows us to essentially homogenize a given variable down to something that can be reduced to something finite. That's kind of the intuition. So what we consider here is, say this plane is one above the origin. So this is our plane. Then what happens is that we consider all lines going through this. All lines. And what happens is that these lines, most of them will intersect just in general, but there are some lines that are just going to be parallel to the plane, if we're considering in a Euclidean way. So what happens is that for those lines, we also again have the point at infinity. Those also generate the point at infinity. And note that the reason that I can define things like this is that it's just really a definition. I'm just saying that there exist points at infinity, and that definition is kind of like how we define the Euclidean plane. We just say there's a given point here. It's so this is not really. It's really just a definition. You can kind of construct any kind of thing. So that's kind of the reason that we're able to do this. So anyways, we have a given point at infinity for any two lines, for any line that's parallel to the plane. And this also generates our given real projective plane. And it also gives us a different way to think about it. What we can think about is just a set of all lines going through the origin. That's kind of the way we can think about the projective plane, the real projective plane, because there's a correspondence between them. And essentially, whenever we have a correspondence, we can just associate everything into that correspondence. So, like in our in the Cartesian plane, we had that there's a correspondence between x comma y and a point on the Euclidean plane. So we could just say that a Euclidean plane, a point on the Euclidean plane could be denoted as x comma y. In a similar way, we can associate that, as we previously associated x comma y to the point, we can associate a line to any point on the real projective plane. So that's why we're able to think of it instead as the set of lines that go through the origin. All right. So now what I'm going to do is I'm going to talk a bit about essentially the coordinates of points in the projective plane. All right, so when we talk about the projective plane, we'll say that any given point is denoted by x to y to z. So x to y to z. Sorry for the bad writing, but right, so the point is going to be known as x to y to z. When we say this, what we really mean is if x, if we're considering a Euclidean point, i.e., in this case, we would have z not equal to 0. So, for example, if we had 1 to 2 to 1 was our point, then what we do is essentially, I guess I'll just say 1 to 1 to 2. Alright, so what we do here is that we scale everything so that z is 1. And what we do is then we associate the given point to the Cartesian coordinate. So if z is not equal to 0, then we can divide by z and say that we can associate this coordinate with the point 1/2, 1/2. So like here, if we had 1 to 1 to 2, what that really means is that on this plane, we're saying if this was kind of the x-axis, this is the y-axis, then our given point is 1/2, 1/2. This is 1, then our point is 1/2, 1/2, somewhere around here. Anyway, so that's whenever z is non-zero. If z is 0, we have a couple of things we can consider. If z is 0, but essentially y is not 0, then we can think about this in a different way. We can think about it as x to 1 to 0. So the way that we kind of want to think about this is that whenever we have a Cartesian coordinate here, the reason that we have it like this is because when we divide by 2, we end up with this coordinate. So while we can't do that here, there is still a property that that would be preserved, the ratio essentially. So the ratio between these two coordinates would be 1 over 1, or 1, and that remains the same for the Cartesian coordinate version, 1 over 2 divided by 1 over 2, or 1. So the idea here is that it's that when we divide by x and 1, we get x. So what this really means is that it's a point with slope x, because if you think about this as say any non-zero real number, it would end up giving us a point that's on the line y equals I should say this on the point where on the direction of the point x, 1, or to be more specific, with slope y with slope 1 over x. Alright, so if we say that this is the point 1 or x, 1, sorry that this is kind of, what I mean here is the line is not supposed to go off the plane. This might just make it kind of look like that. Let me see if I can draw that a little bit better. Hopefully that's a little bit better. But anyways, that's our line here. Yeah, it kind of looks like it's going off the plane, but just this line is supposed to be on the plane right here. Anyway, so it's in the direction x, 1, regardless of what this value is. So when we say 0, we're just going to kind of extend it to that, and hence we're going to say x to 1 to 0. But again, if it's 0, then it's going to like give us a point that's not finite. Like if we would divide by 0, if we were going to divide by z here, then it wouldn't give us a finite point. So the idea is that it'll be associated with this point on that line, the point at infinity on that line. So that's kind of the thing. That's kind of how you should think about that there. And then last thing would be if we had 1 to 0 to 0, since we could say x to 0 to 0, but that would just be scaled down to 1 to 0 to 0 anyways. So if we say 1 to 0 to 0, then what this means here is that, well, essentially, if we're considering the kind of same ratios as we did before, x to y here would be 1 to 0, or that means that x kind of has it's going to be along the direction 1, 0, or along the x-axis. Here when we say 1, 0, the Cartesian point 1, 0. So right here. So it would be along that point. It would be along that point right here, and then again we can't divide by 0, so it'll be the point at infinity along the x-axis. So those are kind of the projective coordinates right here. All right. So as before, when I mentioned this, I said that they're homogeneous. Again, what this means is that if you take any coordinates x to y to z, then you can scale them by any number, any non-zero real number. Since we don't have something like 0 to 0 to 0 would not be defined. All right, so you can scale by, say, factor of lambda. All right. And now, all right, so what we'll be considering next is kind of the ideas behind moving points. So when we're going to consider this, we're going to be talking about how we can consider points in terms of their polynomial versions. So I'm going to start off with an example right here. So we all know the circle is given, unit circle is given by x squared plus y squared equals 1. And we also probably know the parametrization of this. So when we say, here we say x squared plus y squared equals 1. It's the unit circle. So the idea here is that we're going to try to essentially take any given point and parametrize it. So there are a few ways to do this. You can just, there are multiple parametrizations. You can just think of it because Pythagorean triples have a degree of freedom of 2. So because you can say m squared minus n squared, 2mn, m squared plus n squared, and just divide by m squared plus n squared. And you can kind of just take x and y and use the parameter t to end up giving multiple ways to do that. So I'll just go with one possibility. You can say 2t over t squared plus 1, again, because we can take, say, the Pythagorean triple with when we're saying m squared minus n squared 2mn, m squared plus n squared. The idea is to take the Pythagorean triple when we have t is equal to m and n is equal to 1. So here that would be 2t over t squared plus 1. And then here we'd be saying, of course, that's squared. But I'm just going to put this in coordinates form right now. So 2t over t squared plus 1. And then the other one would be, we would say m squared minus n squared. So that'd be t squared minus 1. And then minus 1 all over t squared plus 1. And it's evident that this is going to indeed satisfy it, and it'll give us a parametrization. All right, so right here, what we can think about is, instead of thinking about how the entire curve looks like, what we think about is how this has kind of a polynomial, kind of a similar idea to a polynomial. And what that leads us to think of is the fundamental theorem of algebra. Because the idea behind moving points is that we can take just a few points, and given kind of these expressions, and if we have like some information about them, we should be able to deduce the entire curve. So for example, if we had, I'm gonna explain like a polynomial example, not a curve example yet, because that will requires projective geometry and some additional ideas. So we'll start off with an example of polynomials. So let's say that we wanted the graph of x cubed plus x. So right here, we know that it has degree 3. This polynomial has degree 3. So the question is, how could we deduce it if we knew it had degree 3, but we didn't know the actual polynomial, but we also knew some of its roots? So here, let's say that we don't know what this polynomial is. We don't know what this polynomial is, but we do know that 0 is a root, -1 is a root, or sorry, not -1, I believe that it would be I is a root, and -I is a root. Alright, so here 0, I, and -I would be the roots. Alright, so the question is, would we be able to deduce it based on the fact that it has degree 3? And essentially, polynomials are all the same up to scale factor if we're considering it like that. So we just want to figure out this polynomial based on it's just say if it was monic. It had a leading coefficient 1. Alright, so but the fundamental theorem of algebra tells us that, well, it has root 0, I, and -I. So that means that it's because it has a degree 3, and these are each of its roots, we can write it as x minus 0 times x minus I times x plus I. I'm just going to write this as x squared plus 1, so I don't have to write too much. Alright. So yeah, anyways, what this means is that even though we only knew a little bit of information, we only only a finite amount of information. We had that it had degree 3, it had root 0, I, and -I. We were still able to deduce that this polynomial ended up having this set of roots. So yeah, that so essentially we took the roots and we were able to deduce the polynomial because we also knew the degree. Anyways, so that's kind of the idea of what we'll do eventually end up doing. There will be some degree here, some degree of a moving point, and we'll know that we'll know some set of cases is going to satisfy what we want, and we'll be able to use the fundamental theorem of algebra in some way to prove that that point must satisfy it around the circle. So here our point would end up having degree 2. This is not I haven't defined degree yet anyway, so but what ends up happening here is that our point has degree 2, and we just need kind of 2 points to figure out what this will end up sketching. Depending on the problem. But anyways, the degree will tell us that we only need a finite number of cases to determine the curve that it'll end up sketching. So that's kind of the main idea behind moving points. All right. So we'll begin talking about some additional things, some additional concepts. So what we'll do is we'll talk about projective lines. Moving lines is a different way to say it, but so essentially moving points. So I'm going to first say an additional thing here. So moving points, when we say this here, notice that it kind of has the same homogeneous representation as we kind of talked about before. That's because we had the scale factor of t squared plus 1. But what we do is that we can actually associate it with the projective plane by taking this as having points as having projective coordinates 2t to t squared minus 1 to t squared plus 1. And that would be the point that it would be on the projective plane. So you can kind of see how the projective plane kind of makes this a bit easier, because we can, instead of thinking about fractions of polynomials, we can think about just polynomials themselves, which is kind of the main reason we're able to get a good notion of degree by using the projective plane. All right. So I will I'll talk about the moving lines now. So here, let's say that we have a point A to B to C in the projective as its projective coordinates. Then we define our moving line. Its moving line to be the line AX plus BY plus CZ is equal to 0. So there are multiple interpretations of this line. Essentially, it'll end up giving us a few different things. Anyways, so this will have this will be essentially this is the general equation of a given line, and again, homogeneity is kind of a theme here because we can scale A, B, C, and it'll still give us the same line. So that's kind of the same kind of idea. Scaling the coordinate here ends up giving the same line. The same line scaling line here would get back the same coordinates anyways. So anyways, that's kind of what we'll say as a moving line. And there are some different things you can think about with this. There's a plane that is perpendicular to, but anyways, this is just our definition because it gives us a one-to-one correspondence with lines in the through the origin essentially. So through the origin anyway. So those will be our lines. That's going to be our moving lines. So what ends up happening with moving lines is that, well, sometimes we do have more than just multiple points in a figure. We have some lines in the figure as well, going through 2 points, and we might have another line intersecting it, say here. Then if we had this kind of geometry problem, then, well, computing we'd be able to compute the degrees of these in a straightforward way. It's kind of the thing that we'd be able to do with moving points. But now, when we extend these lines, having to compute that kind of point, the degree of, say, this one, would be kind of, we can't do it without knowing the degrees of these moving lines. And to that end, the line here, and the line here, although we don't know actually what kind of form they'll have, we'll be able to get their degree because we know the degrees of these 2 points. And it kind of might be a bit surprising that we can essentially get the degree of a moving line based on the degree of 2 moving points. And that is a kind of important result that allows us to use moving points in a very interesting way in moving points, in the method of moving points or animation. All right. So again, I haven't defined moving points, or I haven't defined degrees or any kind of notions like that yet, but I'm just kind of giving a general sense of what this means. All right. So now I'll define degrees, the degrees of a moving point. All right, so the degree of a moving point is going to be, we'll say that it's the maximum of 3 coordinates that we have. And again, I'll have to specify this a bit more. So what we're saying here is that if we have a point, if we have that a given point is moving based on a parameter t, just like our parameterization here. So like if you kind of varied t from negative infinity to infinity, you would have like varying moving. The point would be moving. So what happens here is that we'll say that the degree is the maximum of the degrees of the polynomials in its homogeneous representation. And again, as I said before, I'll have to specify this a bit more because they can't have a common root. So because if we had, say, if we multiplied this by t minus 1, t minus 1, t minus 1, they'd still have the same homogeneous representation, but technically if we defined it like that, we'd have higher degrees, and that wouldn't give us a well-defined notion of degrees. So what this means is that we're saying that there's none of these polynomials here have a root in common. And additionally, and you might kind of question why we're saying that they shouldn't have just any root in common instead of, say, a real root in common, because you might think that it doesn't really matter if they have a complex root in common because we can't really factor it out. Well, we can, considering the complex conjugates and conjugate root theorem, but additionally, even if we couldn't, that's an additional kind of point. A lot of this comes from the space CP squared. So we were working, sorry, not CP squared, CP and CP squared, both of them actually. But anyways, so you might be thinking that taking, if we said that they had an imaginary root in common, then it would be fine. Well, technically that is correct. And if we're only working in the real projective plane, but if we were only working the real projective plane, we miss a lot of things, and just moving points are not as well defined as we would want them to be. So what I'm going to say here is that if we're saying that we're going to multiply by t minus 1, notice that although we're having t range from infinity to negative infinity to infinity, what happens is that we'll end up getting bounds on the degree of this at some point. We end up getting bounds on the degree of moving point. So this moving point, we end up being able to bound the degree. And that's the key thing, because we can't bound the degree without having this kind of notion that we divide by whenever they have a common root, just in general, because we work in CP squared because they have, say, like roots maybe I and negative I in common. The reason it's a bound is because it's these are, if we were working in CP squared, we would end up having those roots, and it would be an exact number. But if we're working in RP squared, then, well, those roots don't end up happening because we're ranging from parameters like from times like these, in which like these numbers don't ever happen. And I should probably define CP squared here. CP squared, when we say CP squared, we're saying the complex. Okay, so when I say CP squared, I don't expect you to visualize because I'd be very surprised if you could. This is the complex projective space, or anyways, this, we denote this as CP squared. And what this really means is that we're having the plane C squared, and we're extending it with an additional plane at infinity. So we have C squared with an additional plane at infinity. So this is 4-dimensional. So I just want to make that explicit. It's a 4-dimensional space that you should not be able to visualize. Anyways, so this 4-dimensional space, again, it's kind of better to think about them, the spaces that we have, as triples or tuples of points, rather than thinking about them geometrically, except in the cases of when we're having, like when we're working the reals. So here we would consider it as points, as we could say just A, B, C, D, as a triple of numbers like that. And these, so this would be our quadruple of numbers here in the case of complex projective space. Alright, so this would be our complex projective space, and what happens is that this will have degree 4. It's kind of similar to RP squared, where RP squared had degree 2, while here we have complex numbers, so it would be double that degree, or degree 4. And again, you could say this is actually a homogenized degree 5, but in this case, you should probably think it might be a bit better to think about this as degree 4, just because we homogenize the degree 3 to get degree 2 for RP squared, so that we could homogenize the points. But here it's more of a kind of to make sure that we have some bounds. Alright, and again, C squared with an additional line at infinity, additional plane at infinity. So kind of like RP squared, where we had an additional line at infinity. Yeah, I might not have mentioned that when we say RP squared, there's an additional line at infinity. Kind of, when I said to visualize a circle, this circle is kind of like the boundary of RP squared, of R squared. It's the line at infinity, and that's like whenever we have a point, whenever we have a line, it'll probably go somewhere like here, or might go there. Anyways, RP squared has a line at infinity, kind of similar to CP squared, where they have a plane at infinity. So this might seem a bit unintuitive, but it's kind of, we construct CP squared based on off of an inductive idea. It's kind of, it's not really an elementary thing, but when we have motivation the motivation to construct it is just based on constructing general CP to the nth in an inductive way and RP to the nth in an inductive way. So yeah, that's kind of just the reason. Here we're considering CP squared because it gives us enough, it gives us the variability that we want. Alright, so anyways, this gives us some notions. Anyways, so again, A of t, B of t, C of t, I'm just going to say A, B, C, where A, B, and C are polynomials, such that ABC, GCD of ABC is 1. They don't have any common factors. So GCD of ABC, yeah, this is not very good writing, but anyways, GCD of ABC is going to be equal to 1, is the main point. So I'm just going to delete that because it's a bit messy. So essentially, they have no common collective common roots. They can have pairwise collective common roots, but anyways, yeah, that's the degree of point. So if we had, say, t to t to 1, again, you can visualize this as saying, okay, we'll divide by 1. It's the point t over 1 to t over 1. But what kind of degree does that have? Well, it is indeed degree 1, because right here, our maximum degree here is 1. We have t and t, they both have degree 1. So anyways, you can visualize that as, well, this is the Cartesian point x comma x. So as t moves, so like it essentially moves along the line x, y equals x. It just keeps moving. So you can kind of see why it would probably have degree 1. It kind of just moves linearly. And that's one of the main points here. We have linearly moving points. That's a point of degree 1. Alright, so additionally, we talk about some other aspects of moving points. There are several lemmas that we talk about here. Anyways, that's kind of the gist of everything for moving points, and I'll begin talking about some kind of the results of moving points in some of the next videos. Alright, just in case I missed one thing, I want to say that for moving lines, again, our degree for moving lines, we have there are several ways to define the degree of a moving line. I'll probably talk about it next video, we have one main definition. Shouldn't have said that there are many ways to define it. What I meant is we have one way of defining it, although there are many ways you might try to define it. So additionally, when we say that we have a moving point here, it's kind of just, you would think kind of, if you say A to B to C, it should have the same degree as the moving line ax plus by plus cz equals 0. So that's kind of the main idea. Ax plus by plus cz corresponds to the triple A to B to C, since we have that kind of correspondence. Anyways, that's probably going to be it for this video. So main takeaways: we can define RP squared, point on every direction, and there's a line at infinity, and then we can kind of create Cartesian points and associate them with these with the real projective plane, except it's kind of extended. And additionally, the set of lines going through the origin of the 3D plane has correspondence with our given real projective plane. And we have our polynomials allowing us to get curves with a limited amount of finite information. We have the correspondence between a point A to B to C and ax plus by plus cz. I should make this more explicit. Ax plus by plus cz as the moving line of A to B to C has the same degree as A to B to C. And this will these are kind of some of the first main definitions that should allow you to get some grasp of moving points, technique of moving points animation. And I'll talk about some lemmas in the next video. So, I'll talk about some additional things like linear maps, or how we can have I'll probably try and give some intuition about moving lines and how they'll end up working, and I'll give a clear explanation of how we end up having moving points and moving lines, giving us a way to have to determine a property just based off finite information, property that would have a higher degree based on information of a lower degree. Anyways, thanks for watching. If you like this video, stay tuned for more videos. So thanks.